Okay. So, we will continue the Hamiltonian formulation in this lecture 36 of classical mechanics 1. So, in last lecture we have constructed the Hamiltonian and we have seen the canonical equation of motion. In this lecture we will see that what are the advantage or what are the differences from the Lagrangian formulation to Hamiltonian formulation, and then we will consider several examples to construct Lagrangian for simple systems, and we will see that how equation motion can be obtained. We will compare those equation of motion to those equation of motion in Lagrangian formulation. So, this is lecture 36 and we will continue with the Hamiltonian formulation. So, in last two lectures we have seen that you have this set of qi dot t to Hamiltonian qi pi and t. We can go through Legendre transformation and we find that equation of motion qi dot is del h del pi and minus pi dot is del h del qi, and of course, so these are canonical equation or equation of motion, and also del L del t will be minus del h del t. So, if there is no explicit time dependence in the Lagrangian, your Hamiltonian also will not have any explicit time dependence. So, this we have learned, and now we will have to construct Hamiltonian for different system, but before that let me compare these two formulation. So, comparison between Lagrangian and Hamiltonian formulation. So, first we will do that and then we will move to the construction of Hamiltonian for simple systems. Okay. So, this side I will write Lagrangian formulation and this side I will be writing Hamiltonian formulation. Okay. So, Lagrangian formulations qi dot, or rather let me write, it is a function of qi dot and t. Hamiltonian formulation, it is function of qi pi and t. And qi dot is considered the independent to qi while considering partial differentiation. Okay. And in this formulation qi and pi, which is defined from the Lagrangian del L del qi dot, are considered to be independent variables. So, in true sense, Lagrangian formulation has n number of independent generalized coordinates, but in the Hamiltonian formulation we have 2n number of independent variables qi pi. So, the concept of phase space will be there in Hamiltonian formulation. So, Lagrangian formulation will have configuration space which is spanned by the generalized coordinate. So, it is n dimensional spanned by all generalized coordinates. Okay. every point in the system is represented by a point in the configuration space. So, system every instant of time is represented by a point in the configuration space. On the other hand, you have 2n number of independent variables, n number of coordinate and n number of momenta. So, you can think of a 2n dimensional phase space okay. So, you will have a phase space where it is 2n dimensional. So, phase space 2n dimensional. So, system is represented again by a point in this. Okay. So, in Lagrangian formulation, third point it will get, we have n number of second order differential equation. On the other hand, in Hamiltonian formulation, we will have 2n number of first order differential equation. So, we have advantage of solving first order differential equation even though they are more in number. Okay. So, these equations are qi dot is del h del pi and minus pi dot is del h del qi, and in the Euler-Lagrangian equation is del L del qi minus ddt of del L del qi dot equal to 0. We have already seen that in most cases in the conservative particularly system, Lagrangian is kinetic energy minus potential energy. However, this is not a requirement. Lagrangian should be such that it produce correct equation motion to describe the system. So, fourth point, Lagrangian generally kinetic energy minus potential energy, and in the Hamiltonian formulation, Hamiltonian is the total energy of the system. So, in that sense it is unique because a system has a unique energy. Okay. And these are the points, but again I want to mention that for a dissipative system you cannot have a your Hamiltonian to interpret the total energy of the system. Okay. So, these are the comparison between Hamiltonian and Lagrangian formulation, and now I am going to show you that basically they are equivalent. So, let us consider some simple examples and to establish the equivalence. For example, if we consider the simple harmonic oscillator. Simple harmonic oscillator we have already seen one dimensional. So, let me write one dimensional simple harmonic oscillator. So, Lagrangian we have seen it is half m x dot square minus half m omega square x square. Okay. So, if we find equation of motion for this system will be m x double dot plus omega square x will be equal to 0. So, it is a 1 degrees of freedom. So, you will have only one second order differential equation. So, on the other hand, if we construct the Hamiltonian, so let us construct the Hamiltonian for this system. So, a Hamiltonian for the system can be defined as x dot Px minus L through Legendre transformation. Now, Px will be del L del x dot, which is nothing but mx dot. Okay. So, you will have mx dot square minus half m x dot square plus half m omega square x square. But x dot is also p by m, right. So, this is basically half m x dot square plus half m omega square x square. But I am repeatedly saying that your Hamiltonian cannot be function of x dot. So, you have to substitute this x dot using this relation to write the Hamiltonian in terms of momentum. So, this if you replace, then it will be p square by 2m plus half m omega square x square. So, this is the Hamiltonian for a simple harmonic oscillator. We have seen, we have constructed from the same Lagrangian. So, we expect that canonical equation from this Hamiltonian should be equal to the Euler-Lagrangian equation from the Lagrangian. So, let us calculate the canonical equation for this system. X dot will be del H del Px. So, that we get Px by m and minus Px dot equal to del H del x, which will be m omega square x. Okay. Now, so let us consider this is the canonical equation. So, let us consider this is first equation, this is second equation. Now, if you differentiate again the first equation with respect to time, x double dot will be 1 over m p x dot, and you substitute that p x dot from equation 2, you will get 1 over m, and p x dot will be minus m omega square x. So, we find m get cancel, minus if we bring this side, it will get x double dot plus omega square x equal to 0. So, look at this Lagrangian equation, that this Lagrangian equation is same as the equation we obtained through Hamiltonian. But initially we get the canonical equation which are first order in differential equation. So, this is the advantage of Lagrangian Hamiltonian formulation, and not only that, this also gives you the equivalence between Lagrangian and Hamiltonian formulation. So, any other problem also you can find that the Lagrangian and Hamiltonian formulation are equivalent, and over and above you will have advantage of solving first order differential equations. Okay. So, now let us consider few examples to construct Hamiltonian. For example, the pendulum problem, simple pendulum problem that we have discussed many times. You have a mass attached to a fixed length string, and the mass is having a oscillatory motion in the vertical plane. And we have seen that if this angle with the vertical is theta, then the Lagrangian is ml square theta dot square ml square theta dot square plus mgl cos theta. So, this is the Lagrangian. We have half ml square theta dot square mgl cos theta. Okay. And then if we calculate our Hamiltonian, so Hamiltonian is expected to be function of p theta, because it is 1 degrees of freedom and theta. Okay. So, it will be p theta theta dot minus L. So, let me calculate it for you, and p theta is del L del theta dot, which will be m L square theta dot. Okay. So, this is basically theta dot is p theta minus m L square. This will use later, but now what happened, you have p theta is m L square theta dot. So, let me write this Hamiltonian will be H equal to m L square theta dot square minus half m L square theta dot square minus mg L cos theta. Okay. I have substituted the Lagrangian. This first two term will combine to half m L square theta dot square minus mg L cos theta. Now, you can see that if I use theta dot equal to p theta by m L square, so it will be p theta square by 2 m L square, theta dot square p theta square by m L square, 1 m L square will get cancelled. So, times mg L cos theta. So, this will be the Hamiltonian for a simple pendulum. Okay. If you have difficulties and questions, please raise in the discussion forum. And if you find the equation of motion, this Hamiltonian will give you the equation of motion from Lagrangian formulation theta dot plus g by L sin theta equal to 0. And canonical equation you can find. So, this is the equation from Euler-Lagrangian equation from Lagrangian, and from canonical equation if we consider theta dot will be del H del p theta. So, it will be p theta by m L square and minus p theta dot will be del H del theta, which will be there is a minus in the formula, cos theta derivative will be minus. So, it will be mg L sin theta. So, now if you make a theta double dot, it will be p theta dot plus m L square, which will be minus mg L sin theta by mg L square. So, again you will find the same equation theta double dot plus g by L sin theta equal to 0. So, again this establishes the equivalence between Hamiltonian and Lagrangian formulation, but you do not need to combine this canonical equation, you can directly solve canonical equation to find the solution. Okay. To construct the Hamiltonian, particularly in different coordinate system, you need to know the kinetic energy term in kinetic energy term, which in Cartesian coordinates is half m x dot square y dot square plus z dot square. So, this is the kinetic term in the Cartesian coordinate, and in terms of velocity. So, if you change to momenta, it will be 1 over 2 m p x square plus p y square plus p z square. These are the momenta for conjugate to x, y and z. So, this will be the kinetic energy in terms of momentum. Now, if we want to use different coordinate system, for example, if you use in cylindrical coordinates, we will have you just verify yourself, but in cylindrical coordinate this will be using when solving many problems will be p r square plus 1 over r square p theta square theta or maybe phi in cylindrical coordinate r, phi and z. So, let us write phi and p z square. So, this will be the kinetic energy in cylindrical coordinate. Similarly, in spherical polar coordinate, okay, spherical polar coordinate, it will be h will be 1 over 2m, spherical polar coordinates is r, theta, phi, cylindrical coordinates was r, phi and z, right. And you should remember the relation between Cartesian and this coordinate system. So, it will be p r square plus r square p phi square plus r square sin square theta, no, p theta square, and then you will have p phi square. This is a mistake. Let me correct. Yeah, so this is not correct. Yeah, so let us use a different pen. Okay, so in the spherical polar coordinate, 1 over your Hamiltonian will be 1 over 2m, and then p r square, then 1 over r square p phi square plus 1 over r square sin square theta p phi square. This is p theta and this is p phi. So, this is the kinetic energy term in terms of momentum in spherical polar coordinate. You can calculate this. Now, we will consider few examples, 1 or 2 more examples to calculate the Hamiltonian from Lagrangian, that steps I mentioned. So, let me illustrate some of them. So, for example, as I mentioned earlier that Lagrangian, so example for a free relativistic particle. So, for free relativistic particle, Lagrangian is minus m0 rest mass and c square velocity of light root over 1 minus v square by c square. So, if a free relativistic particle has a velocity v, then this is the Lagrangian, okay, in one dimensional. So, we are considering, let us one dimension, so velocity in some particular direction. Now, what will be the Hamiltonian corresponding to this? Okay. Note that this Lagrangian was not in the t minus u form. So, let us apply the Legendre transformation method to construct the Hamiltonian. So, momentum, first Lagrangian is there. So, let us find momentum conjugate to the coordinate. So, it will be p will be del L del v. So, which I can write minus m0 c square by 2 root over 1 minus v square by c square times minus 2 v by c. Okay. So, if I differentiate, so minus minus plus, and then it will be m0 v, this is c square. Okay. So, it will be m0 v, 2 also get cancelled. So, root over 1 minus v square by c square. Okay. So, p is this. So, now we defined your Hamiltonian is p v minus L. So, p is m0 v. So, m0 v square by root over 1 minus v square by c square minus m0 c square root over 1 minus v square by c square. So, if we simplify this, it will be m0 v square minus m0 c square 1 minus v square by c square divided by root over 1 minus v square by c square. Okay. So, there will be some cancellation, say this m0 v square. So, this minus minus plus, oh, there is already a minus. So, this term will be plus, Lagrangian itself has a minus. So, this term will be plus. So, you will have m0 v square term will get cancelled. So, we will remain with m0 c square times root over 1 minus v square by c square. So, this is our Hamiltonian, but we have to eliminate our v in terms of so this is the Hamiltonian after using Legendre transformation, but we have to eliminate v in terms of p using the relation I already mentioned. So, this is the relation, we calculate. So, using this relation we should eliminate this. Okay. So, let us start from that relation, p equal to m0 v by root over 1 minus v square c square, right. So, let us simplify this by making a square. So, square and then multiplying with c square, we will get m0 square v square c square divided by 1 minus v square c square. And now, if we add p square c square plus m0 square c to the power 4. So, let me write m0 square c square v square by 1 minus v square c square plus m0 square c to the power 4. Then we will find that, let us take m0 square c square common, and you will find v square by 1 minus v square c square plus m0 square m0 square I have taken common c square. So, this is only c square. Okay. So, you will find m0 square c square v square times c square into 1 minus v square c square. Okay. So, you will get and divided by the denominator will have denominator will have 1 minus v square c square. So, m0 square c square will be, if you multiply, then it will only v square plus c square minus v square divided by 1 minus v square by c square. Okay. So, you will get m0 square c to the power 4 1 minus v square by c square, which is nothing but equal to p square c square plus m0 square c to the power 4. So, from momentum relation of simplification we found that this. So, if we substitute this, so our Hamiltonian will be root over p square c square plus m0 square c to the power 4. So, in this case we find that the relativistic energy of a free particle. So, Hamiltonian is relativistic energy of a free particle, but please note that our Lagrangian was not T minus u form. Okay. So, we will stop here in this class, and in the next class we will take a tutorial class. We will solve few more problem, and we will consider the Hamiltonian for the charged particle motion in the electromagnetic field. So, bye for now. So, we will consider more things on Hamiltonian in next class. Okay, bye.